Now in section 2.3, we've got a decision to make again, because we're talking about functions. Now you've met the idea of functions, I'm sure, before, but there is a more A-level way of thinking about functions, and this sort of picture here you may not have seen. And in this particular chapter, we don't have to do a great deal with it, but when you come around to looking at functions and domains and ranges, that's one of the trickier areas of the syllabus. So getting an idea of functions in what I'd call a sort of A-level way of thinking about them is worth doing. If you're using these videos just to revise your quadratics and make sure you know how to complete the square and so on, you may want to fast forward the first bit of this, or you may even be happy. If you know how the f of x, g of x function notation works and you're comfortable with that, then exercise 2e can just be seen as a sort of quadratics exercise, but with f of x equals instead of 0 equals or y equals or something like that. Conceptually, though, this is quite an important part of it. You may find that if you were struggling with quadratics, you know, if you were in year 13 resitting, maybe this is the bit that you didn't quite understand last time, because you can answer the questions without fully understanding this bit on this chapter. But when you get further through the AS syllabus and into the A-level syllabus, if you didn't quite understand some of the ideas in this section, that might be what's messing you up, and it might be the thing that you didn't realise you'd missed out, because you don't need them right here on section 2.3, you need them later on in the course. So it's a tricky thing to give you advice on exactly what you want to listen to, but here we go. Here's our idea of a function. So you may be thinking of a function, most people are thinking of a function at the start of an A-level course or from a GCSE course or something that looks like this, right? We've got an x-axis and a y-axis, and we've got some sort of line on the graph. But let me give you another way of thinking about a function, which would be like this. The x values are all here, right, in a big bag, and those x values are all numbers. And each one of those x values, if I pick one of those x values here, is paired up with one of these y values. Now it turns out that here, this bag full of x values the x values are all numbers, and the y values are all numbers as well. For a function, it doesn't actually have to be numbers. I can have a function that starts with an object, a mathematical object, and pairs it up with another mathematical object. What we do often with functions is we pair a number up with another number. Okay, so if this function is the function f of x equals x plus 2, if I start with the number 2, I pair it up with the number 4. Okay? That is another way of thinking about functions. It's a pairing up of two values. The value that you start with is in a big bag. A set is the proper mathematical word. It's in a set of things which we'll call the domain, and the value that you finish with is in a set of values in a set that we call the range. Okay? Now, this pairing up, we can talk about sort of starting and finishing, because we need to have the pair in order. This pair 2, 4 is different to the pair 4, 2, okay? The x value and the y value, the x value is the one that comes first in the bracket, the y value is the one that comes second. So we often think of this as not just a pairing up. I've drawn an arrow on this end and an arrow on this end. We often think of a function as a sort of moving from the domain to the range. And if you look in the diagram in the book, all the arrows point right to left into the range. So we often talk about mapping the value 2 to the value 4, okay? We often talk about there being a sort of motion from the domain to the range set. So I said we could have a function even if it's nothing to do with numbers, right? So what you could have is your domain could be the set of all polygons, and the range could be could be numbers again, and I could take, say, a triangle, and I could say what we're going to do is count the sides on the polygon, and that could be our function, couldn't it? So a triangle gets paired up with a 3, a quadrilateral gets paired up with a 4, and so on. So I've still got a pair of objects, one from the domain, one from the range. The domain is the set of polygons, and the range is the set of, well, in this case it's going to be numbers which are whole numbers, 3, 4, 5, and so on, okay? So your domain set is the set of values that you can put into your function. The range set is the set of values that you can get out of your function. Often with a function, and with any function that we can draw on a set of x and y axes, the domain set is numbers and the range set is numbers. It might be that the domain set and the range set aren't all numbers. Okay, so if I'm looking at the function f of x equals x squared, then the domain set could be all numbers, all real numbers, and that has the symbol this. So that, if you've not met it before, that r with an extra line means all numbers on the number line, all real numbers. Your range set has got to be positive numbers. If you square something, you're going to get a positive answer. So for this function, the domain is all real numbers, and the range is all real numbers that are greater than 0. Okay? So even though any function that we can draw on a set of axes like this, the inputs and the outputs have to be numbers. The inputs and outputs don't have to be all the numbers. And when you get onto later in the course, we look at how to think about domains and how to think about ranges and all that sort of thing. I'm not going to go too far into it now, otherwise we'll end up doing a whole chapter from a different part of the course. But what's important is this idea of you have a domain and you have a range, so you have inputs and you have outputs. A function can be thought of as pairing up things in the domain with things in the range. If we're thinking of them as pairs and we write them as coordinate pairs, it's important to identify somehow which is the input and which is the output. And the way that we do that is that we write the input first and we write the output second. And we're familiar with that because the input is the x value, the output is the y value. That way of thinking about a function is the same as this graph, because we measure the input as an x as a distance here, and we measure the output as a distance here. And so this point here has the input and the output in the horizontal and vertical distances away from the origin. Okay, so we take those two numbers and we turn them into distances, and that's how a function like this represents a function that we can think of like this. You may have met this idea as well when you very first saw algebra back in year 6, 7, 8, and you may have seen something like this, which says, okay, we've got a box and I put something into the box. So if I put a 1 into the box, then what I get out is a 3. If I put a 2 into the box, what I get out is a 4. If I put a 6 into the box, what I get out is an 8. And then you work out, well, what the box does is adds 2. Okay? So the other way of thinking about functions is like this, what's sometimes called a function machine or an algebra machine or something like that. And this notation just says the same thing. This says if you input an x, the output is that x plus 2. Okay? So if, with that notation, if I take f to be that function, then if I input a z, the output would be z plus 2. If I input a 4, the output would be 4 plus 2. If I input an x plus 7, then the output would be x plus 9. Okay? So when you see this function notation, the thing in the brackets is the input, the thing on the other side of the equal sign is the output, and if we want to describe the function in general, the thing in the brackets is usually an x, and the thing on the right hand side tells us what you do with the x. It's an algebraic expression, it's a set of instructions for what to do with the x to get an answer. So that is the new way of thinking about functions, which you may not have seen before. The domain set and the range set. The domain set is the set of possible inputs. The range set is the set of all the values that can be output from that function. And a function is a pairing up of things in the domain with things in the range, or a mapping of things in the domain to things in the range. So, how do we deal with that? In the examples, well, f of x equals 2x minus 10 and g of x equals x squared minus 9. So this is telling us two different functions. One of them is called f, one of them is called g. If I input an x into my f function, so whatever your input is, you need to times it by 2 and then take away 10. So if I'm looking for f of 5, I need to do 5, times it by 2 and then take away 10. My g function is the x squared minus 9, g of x, they're telling us is x squared minus 9, so that means take your input, square it, and then take away 9. So g of 10, if I input a 10, I get 100, take away 9, so I get 91. The next thing is asking us f of x equals g of x. So that is saying, well, when is the output of the f of x function equal to the output of the g of x function? Okay? And then that gives us an equation. That's a quadratic equation, and we can rearrange it and solve it like a quadratic. So what they're doing in this part of the chapter is they're trying to get you used to, and in fact they're doing this in the first half of exercise 2e, they're trying to get us used to this way of thinking about a function, this function notation, and this way of thinking about it. But that's all. They're just introducing the notation. It does an awful lot more, this function notation and this way of thinking, but that's all we do for the moment. Now, as I said at the start of the video, if you're coming back to this, having got stuck later in the course, it may be that was the bit that you were missing, because when you come back to these functions, the notation does lots more, but they're assuming that you understand that much, and then plunging us into f's of g's of and f inverses and that sort of thing. But we'll not worry about that for now, because it's not part of this chapter. So if you're doing this for the first time, that's all we need to know. And that means that we can phrase questions in function notation. So example 9 is not really a new question. It's just phrased in function notation. So f of x is this quadratic. Rewrite f of x in this form. Well, that's just saying take x squared plus 6x minus 5 and write it in this form. And hopefully we recognise this is completed square form. So that will stump a lot of people. All it really means is take that quadratic and complete the square. I should mention this little symbol here. And that is that if we're thinking of this function notation, we have to tell you what your inputs are, okay? I can't just say, well, f of x is this. When you put something in, it outputs this thing, without telling you what sort of object you can put into it. Because in theory, we could have a function where our inputs are shapes or anything else, right? So we have to say, things that I'm calling x, possible inputs, are contained in the numbers, right? So this is our r, this is our real numbers, this is our number line symbol. So this just says f of x equals x squared plus 6x minus 5, and anything that I'm calling x is a number. That symbol is a contained in symbol, or is a member of symbol. So x is a member of the real numbers, or x is contained in the set of real numbers, or in other words, x is a number, okay? So hence or otherwise, find the roots of f of x. So here we go. We need to talk about the difference between functions and roots and equations and solutions and things. So f of x. Now again, philosophically, this is fiddly, and practically, it's sort of fairly straightforward. So f of x is that. So the roots of this function are the solutions of the equation, that, okay? Now, a lot of people say, well, that function is the same as this, but look at it, it's different. And the reason it's different is because here, the x can be any value. X is any real number. You can take an input, you can take an output. If you have this thing here, this is an equation. There's only two values of x which make this thing a valid equation. Any value of x can be input into the function and outputted, okay? So we need a special bit, because we've got x squared plus 6x minus 5, and one of the things that we sort of want to do then is solve a quadratic with that expression in it. We have a special name for it. The roots of this function are if you take the output of the function and you put it equal to 0, and you find what input made that 0, okay? So for the roots of a function, put f of x equal to 0 and solve. That's just something we need to know. And by the time you get to the exam, or in fact, by the time you finish exercise 2E, that should be so familiar that you've almost forgotten that there's any thinking to do there. But it will help if you remember this thing and this thing are not the same. This is an equation, this is a function. If I want to turn the function into this equation, then I'm looking for the roots of this function. That's sort of, it's important at the level of identifying what these mathematical objects are, okay? So find the roots of f of x. So that just says solve that equation. Leave your answers in surd form. We should be used to doing that by now. Write down the minimum value of f of x and state the value of x which occurs. Right, so writing down the minimum value of f of x. Now this is where completing the square comes in handy, and we'll see this in section 2.4 as well. If I've got, in fact, you know what, I'm going to do this on a separate video because it comes up in so many different places, and it's the thing that people get messed up on. So other than that, so in the next video I'll do how to find minimum values of quadratics. Other than that, this chapter, this exercise on this chapter is just trying to get you used to this function notation. It's trying to get you used to thinking in function notation terms, like in exercise 1 and in question 1 and exercise 2e. And then it's trying to get us used to this idea of finding roots and minimum values and all the other things that we can do with the techniques that we've seen so far in this chapter. Okay, so next video coming up on minimum values of quadratics.